Hello everyone, my name is Aditi Sanjay Gandhi and I am very much excited to share my internship experience in embedded system. Over the past month, I worked extensively on microcontroller programming, real-time interfacing and embedded application. So in this presentation, I will cover everything I learned in this internship. So first of all, what are the embedded system? Embedded systems are specialized computing systems designed to perform specific tasks. They are like a mini computers built in devices to control functions, monitor inputs, or process the data. For example, it's included in smart applications, traffic lights, medical devices, automotive systems. In this system, it uses a microcontroller microprocessor along with software to control hardware efficiently and reliably. Now we will see the types of embedded system. Here in this embedded system, the standalone type, real-time, network and mobile system. In the standalone system, it is work independently. For example, microwave, controller or simple digital watch. It is focused on dedicated tasks and no external communication is needed. Then, in real-time system, it processes the data and responds within a strict timing constraint. For example, this system using airbag sensor in car or industrial PLC controller. It is a deterministic behavior is crucial for safety or performance. Then, network system. What is network system? It connects to network like LAN, WAN or IoT. For example, it is using smart home thermostat or remote monitoring devices. It's enable data exchange and remote control. Then in mobile system, it is a portable optimized for a low power and size. For example, it is used in a smartwatch or handheld GPS unit. It balances the functionality with battery life and mobility. Then in the next slide, we will discuss the component of embedded system. Here is a component of embedded system: microcontroller or microprocessor, memory, input devices, output devices, power supply, and the software. Here, in this diagram, we will see the detailed components of an embedded system. Here is a microcontroller, which is connected to AD converter, then RTOs, then actuators, then DA converter, then hardware, then sensors. This all of this is the component of embedded system. Now discuss each component in detail. First is microcontroller and microprocessor. The role of this microcontroller and microprocessor is this is the CPU of the system which executes the instruction and manage the operations. Then the memory we store the program and data. Then in the input devices, it's provide the input to the systems. Example of these input devices like sensors, switches. Then output devices. Example of output devices is LED, LCDs and etc. which display or act on the output. Then in the power supply, which provide the regulated voltage, often a constant in the battery power devices. Then in software, firmware, which is the embedded code that control the hardware behavior. So that's all about the component of embedded system. Then in the next slide, we will see the C programming basics for the embedded system. In this internship, I learned the C programming basics to advanced level. For the embedded system, it is really essential to learn the C programming. The question is, why C language is used? Here it is a portable, efficient and gives the hardware control. Let's see on the focuses on some key point areas in this C programming. There is a data types, pointer and registers, then bit manipulations, then memory, interrupt optimization. This all of these things which are manages in C programming for the embedded system. Then in the next slide we will see what is microcontroller. Microcontroller is a single chip computer. It contains CPU, memory and the input output ports on one chip. In a single chip, all these things are contained. Then it is used to control a specific task in embedded system. It is commonly found in home appliances, automobiles and gadgets. So let's see in the next slide the components of microcontroller. Here is the components of microcontroller. There is CPU, memory, I/O, input output ports, then timer counters, then serial interfaces and ADC and DAC, which convert the analog signal to digital signal and vice versa. Now let's see the types of microcontroller. As we know that microcontroller, they are the brain of our embedded system. Here in this microcontroller, first is 8-bit microcontroller, which is a simple, low power and widely used microcontroller. For example, in Arduino's AVR. Then in 16-bit microcontroller, it is more processing power used in industrial applications. Then in 32-bit microcontroller, it is a high performance complex task. For example, in ARM Cortex-M. Then this microcontroller's architecture based on Howard was and von Neumann's. So here I mention here. Now if you see, it's about the microcontroller architecture. So usually microcontroller follows two primary architecture. One is von Neumann, another is Howard architecture. Let's see how both are different with each other. Let's see in detail. In this architecture, in the von Neumann architecture, it uses a single memory for a program and data storage. Then it is a sequential instruction executions. It has a simpler design but slower due to the memory bottleneck. But in the Harvard architecture, it is separate memory for program and data storage. In this architecture, there is a parallel instruction execution and it is a fast performance commonly used in embedded system. This is a von Neumann and Harvard architecture. So in the next slide, you will see the PICSimLab IDE and development of the environment. In the PICSimLab IDE, it is an integrated development environment developed by a microchip technology for writing, compiling and debugging the program for a microchip controller. Then let's see about the X8 compiler. This is a compiler for 8-bit PIC microcontroller. Then we will use the PICSimLab stimulator. In the PICSimLab stimulator, it is a free stimulation software used to design, test and debug the program for PIC controller without needing any physical hardware. Let's see this PIC16F8778 microcontroller overview. This is a 8-bit microcontroller. It has a memory of 14 KB flash, 368 byte RAM and 256 byte EEPROM. Then it has a 33 input output pins. Then its peripheral, talking about its peripheral, it is a ADC 10-bit 8 channel. Then it is used 3 timers. Then in the operating voltage, it has a 5 volt and clock up to 20 megahertz. Then talking about its applications, it is used in robotics, automation, home appliances and embedded projects. Advantages of this microcontroller is low cost, easy to program, and it is versatile. In these slides, we will see the peripherals used in the project. In this project, peripheral use there is switches and keypad, CLCD display, and timer and buzzers. Here, the next slide, we will see the LED programming and switch programming. In my internship, I learned the LED programming and switch programming. In the LED programming, that is interfacing LEDs with microcontroller, writing a simple LED on a program, which is concept of digital output. Then in switch programming, is the interfacing of push buttons, switches, reading digital input, switch disbouncing, which is a software method, and which is combining switches with LEDs for control. Now we will see the matrix keypad interfacing. In the matrix keypad interfacing is a set of buttons arranged in rows and columns for input 7 controller pins. The working principle of this matrix keypad interfacing is key connects a row and column which the microcontroller detects to identify the key. How it works? Keys are arranged in the rows and columns, then microcontrollers scan the rows or columns to detect the key presses. Let's see the steps to interface. First, configure rows as output, column as input, or vice versa. Then in second step, scan the rows one by one and then check the column states. Then in third step, debounce the keys. Then in fourth step, map key presses to values or actions. It will use in pin entries, calculator, telephones, embedded projects, or input and output control. Then in next slides, we will see the interrupts in embedded system. Basically, interrupts in embedded system are like a notification for the microcontroller. Like, hey, something happening, handle it, like that. So what are interrupts? The signal to the CPU that an event has occurred. CPU stop current tasks, jump to ISR, which is interrupt service routine. There are two types of interrupt: hardware interrupt, which is external event, and second is software interrupt, which is triggered by code. Interrupt service routine is a short, fast, and no blocking calls. It is used in some cases like responding to the external event quickly or a timer for a periodic task. This is all about the interrupt. Then, in the next slide, we will see the timers in embedded system. Timer in embedded system are like your phone's alarm. They help to manage time-based tasks. First of all, what are timers? Hardware counter that trigger the event or interrupt, which is used for delay, PMW, frequency measurement, and etc. The working principle of the timer is count the pulses from the microcontroller's oscillator that can generate a delay or trigger the periodic interrupts. There are some types of timer like a basic timers, PMW timer, watchdog timers, and real-time timers. There are applications in LED blinking or timing event, then digital clock or stopwatches. These all the applications of the timer. Then see the micro oven project overview. In this internship, in last, I'm make the micro oven project. In this presentation, I will explain the micro oven project. First of all, we will see some overview of this project. In an embedded application that control the micro oven operations, microcontroller manages cooking time, power level, and user interface. Let's see the working principle of the micro oven project. So, in this project, A micro oven works by using a magnetron to generate the microwaves, typically at the frequency of 2.45 GHz. These microwaves are directed into cavity where the food is placed. The microwave penetrates the food and cause the water molecules in the food to rotate back and forth, generating the heat through the dielectric heating. Then, the heat is then distributed through the food via conduction and convection. Then the process is this overall process is controlled by microcontroller that manage the magnetron power output, cooking time, and safety features like door interlocks and thermal cuts off. Then the turntable ensures over the heating of the food. This overall is a clever combination of electronics and physics to quick heat up the food, but it is a physically operation of the micro oven project. But with the help of PICSimLab, how it will work. So, we are stimulating a microwave oven project using PICSimLab. The PIC controller is the brain. It reads input from button, control the magnetron powers, update the display and handle the safety feature like door interlocks. The stimulation let us test all this logic virtually before the moving to real hardware. It is a great way to learn the PIC programming and test ideas quickly. Now we will see the future scope of microwave project. It is smart connectivity, then voice control, energy efficiency, then AI based cooking, then safety enhancement, and last one is integration with the smart kitchen system. That's all about the future scope of the microwave project. Now we will see the live demonstration of the microwave oven project. Before you see the project demonstration, I already opened MPLab ID, so where I wrote the code for the micro oven using a multiple source file. So this project consists of so many files. So before you see all the files, let me give a brief introduction of the files which I have used. One is mainc and one is manage. Where a source file and the header file which handles system initialization and peripheral setup and the main control loop and control one micro one. See, then after that CLCD which control the LCD display handling message and status updates, and where we have ICR dock which is implements the interrupt services routines for a safety mechanism and real-time operation, and I have a matrix keypad C or matrix keypad H, so which process user input for a keypad allowing section of cooking modes and the time adjustment, and we have a timer C or timer H which manages the countdown timer, ensures the accurate cooking duration. So now I will walk through the key section of the code. So is main C and microcontroller initialized and peripherals such as a LCD keypad and timer are configured the main control. Loop continuously monitor users input and system status and the micro and different cooking modes like a micro grill and connection and handle based on the user selections function. So this is a code where I write here. Then after that I upload this my micro oven project code in PICSimLab. First of all, let me first introduce you what is a PICSimLab. So this is a PICSimLab. In this PICSimLab, first of all, I choose the board. This is a PIC Genesis. Then I choose the microcontroller PIC16F87A. Then after that, I will choose the load hex file. In this load hex file, I upload the hex file from here. This file I am going to upload. Then I set up the clock which is already on a 20 megahertz. Then I choose the LCD display which I have 16:4 here. Let's see why use the stimulator actually when developing embedded system Testing directly on hardware can be difficult, and even there is always a risk on the damaging component, right? And even debugging can be time consuming. So that's why where PICSimLab comes. And so it is an open source simulation platform that allow us to test, debug and refine microcontroller based project without needing any physical hardware. So what is PICSimLab? So PICSimLab is a microcontroller stimulation environment that stimulate the different P controllers microcontrollers like the P16F87A and P18F452, which are commonly used in embedded systems. So with this we can test our embedded code before flashing into a real microcontroller, and even we can stimulate the peripherals like LCDs, keypads, buzzers and relays. And we can debug errors safely without damaging real component, and even we can quickly modify and test code without rewiring circuit, and we can also analyze circuit behavior and verifying a logic before deployment. So using a PICSimLab, I can show you how the microwave oven works step by step, just like a real hardware prototype, but without needing a physical step up. So now let's take a closer look at the stimulator and find a different part first. If you see the top left, that is a green screen which are called a LCD display, liquid crystal display. Here it is 16 by 4 cross character LCD base based on HD 44780 driver. So it is used to display system messages, and next bottom left number pad 12 hashtag. So all these are all called matrix keypad. This is a 4x4 matrix keypad acting as a user input interface. And the next middle section you will see a small red headlights. So these are all the LEDs. So the LED represent the different status indicators. Then next top right near the fan and the heater labels, if you see, these are called cooling fan and heater. So the fan can is stimulated where to show how the microwave cools down after the operation, and the heater turn on during cooking, and it is a link to the selected power level. And right side two large white blocks read. So this is stimulate the real relay switches. This is a real relay switches that turn on or off the microwave heater and the fan. So when I press this start button, press the start button, the relay activate powering the heater. When I press stop, the relay cut off the power supply. And the next near the fan and the heater section we have the buzzer. This is a buzzer. This work as an alert system. It sound when a cooking start or stop when cooking time finishes. When an occur like an light. And next bottom right we will have a black IC label peak. Here IC PIC16F8778A. This is a microcontroller where we pick. So, as we know that it is a brain of the entire system, so it runs the embedded C code that have written in MPLAB, and then I uploaded in the form of hex file. It is process input from the keyboard update, then LCD control the relay and ensure the safety mechanism work properly. And next we have bottom right blue button label reset yes. If something, this is reset button. If something going to be wrong, then we will use this reset button. Restart the program. Then we can restart our program and we can see here. Now let's start our demonstration. First of all, we will see a powering on microwave oven. After some time, available modes like cooking modes, which are like micro mode, then grill mode, then convection mode, then start mode. First of all, I will choose the micro mode here. We can see on the display, we have to set the time. First of all, we will clear here. The star button used for a clear if I write some number, but I don't want this, like this, but I don't want this, then I click a clear button where we can reset this time. Then if I choose a 20 second, then hash word is for enter, then it will start. If you have to start or resume, you can click a phone number button. Then if you have to pause this, you can use the fit, or for stop we can use a 6 number button. I am going to stop here. Then in the grill mode, I going to choose a 30 second. Then after that I enter it. Here after time stop, its time is up. Then in the convection mode, I set the temperature on a for example 50 degrees Celsius. Then I enter the button. It gives a 128 second. As we see, it display like a set to first of all we will set the temperature in Celsius. Then it gives a 180 seconds. Then after I press the hashtag, so now you will see that it display the preheating time, which is a default time that I will this is set up. Then let the countdown complete. So once the timer reaches to 0, it will display the message to the user in the interface LCD display, that is timer, which is means the enjoy your meal. Now it written enjoy your meal. First of all, we have to complete this timer. Let's wait. let's return back to the main menu. We will come here on the main menu. So if you go for a start last mode, if you click on that again, it start the timer here. This will be happen again and again. The below done we have behind option to resume, pause, stop, or the same operation which you have done in the previous mode. That is a micro mode. Then green mode and convention mode. So the fan will be operating while the countdown time start. Always so. Once it done, it will be displayed time up, and so you can enjoy your meal. So this is how my project works. So I conclude my demonstration of the microwave oven project. So this system successfully handle a real-time cooking, control a safety mechanism, and user interaction. So there is a chance. So there is a chance. So there is a chance for a future improvements could include like IoT integration from remote control and AI based cooking adjustment. Like, so I'm done with my demonstration. So I'm very much thankful to all of you. You have to watch with so much attention and patience. I'm very much thankful to everyone. Thank you.